So if we're going to draw out what we're seeing with Homer running away from this street lamp, this is the sort of thing we're looking at. Okay, we got Homer running away. But do you see the geometry of what's really pictured here? Because notice, there's some triangles involved here. In fact, while this is a great artistic way to look at it, it's maybe not the most helpful way to look at it. Because in order to deal with the math, I want to strip it down to bare bones here. So I'm going to draw it out looking like this. And so you'll notice, like, here to here, there's my shadow. Here's Homer standing here. But by drawing it just as lines, it makes it a little bit easier to focus on the geometry of it instead. Now, the big question here, and one that we've kind of looked at before but haven't as explicitly dealt with before, is we start by trying to figure out what is actually changing with time here. And there's really two main quantities that we have to worry about. The first one is given to us as a number in the problem, the 8 feet per second. What is changing at a rate of 8 feet per second? Can you see which length that is in the picture? I hope that right now you are envisioning this. This distance right here is the 8. Because you'll notice, he's running away from the street lamp at that time. And so that distance right there is getting bigger by 8 feet per second. Now, I went ahead and labeled it D for distance. Why? I didn't have any better ideas. You can call it something different if you want to, but we need that as a variable. The other thing that's changing, well, as he's running away, what else is changing then?
Where he is.
Well, what are we asked for? How fast will the length of his shadow be changing? And so, any rate that we're given, we want to give it a variable name. We also want to give a variable name to whatever it is, whatever rate we're trying to find, because we need to make sure that these actually become rates when we find a derivative. Well, the other one then is going to be the shadow length. And so I'm going ahead and using D and S for distance and shadow. Nothing magical about those names. But you notice down below there, I wrote out what they represent just to help myself remember. This is what I'm really talking about. It's also going to make sure that I don't all of a sudden think that D is like this whole length or something like that. And so you notice this little comment on the left-hand side whenever we want to set up an equation for one of these types of problems. And by these types of problems, I mean a story problem where we're going to find the derivative. Anytime you do that, you give a variable name to anything that is changing. Anything that is a rate in any way, that has to have a variable name. And if you remember that, these things get a lot easier. So, let's go ahead and deal with our picture now and fill it out more fully. Because I figured out I need to call those two variables. But I got a whole bunch of other information. So, I know Homer is 6 feet tall, so I'm going to go ahead and label him as 6 feet tall. Then, he's running away from an 18-foot tall street lamp. Okay, so I'm going to go ahead and label that height as 18 feet. 18. We know his rate is 8 feet per second. So I'm going to go ahead and label that down here that he's moving this way at 8. And I want to make sure that I remember that is just this distance here. So I'm going to go ahead and label that. So I remember that it's that distance that's changing. Because if we mix up what it is, then it's going to be causing us lots of problems. Okay. Then, how fast will the length of the shadow be changing when he is 100 feet from the light? So that tells me that we want to know what happens when D is 100. Now, I haven't written the units on there. That could potentially lead us into trouble. And so, go ahead and put them on there because it'll help you remember which ones were lengths and which ones were rates. All right, now that we know this, I can now worry about how do I set up an equation. Now, there's lots of things that could tempt us that won't actually work out well. Like, for instance, you might be thinking, let's use Pythagorean theorem. Because we used that on those ladder problems we were looking at last week. But we don't want to here. The reason is because we don't know what the hypotenuse is. The hypotenuse, we don't care how it's changing. And so I don't want to have to create an equation that introduces that as another issue. because then I'd be trying to figure out two things. And if I'm trying to figure out two things, I'm not going to be able to do it. I can only figure out one thing at a time. So Pythagorean theorem is out. Some of you might be thinking, well, okay, then let's find out what the angle is, and we can use our trigonometry skills. Again, I mean, you can figure out stuff that way, but it's totally unnecessary here. We don't need to do it.
Totally, I agree.
Instead, what I see here is two triangles. Specifically, these two triangles would be similar triangles. And I know they're similar because they're both right triangles, and their sides are proportional because they share the same angle. Here, basically, by angle, we have similarity, to bring you back to your geometry days, right?
I love this.
So, we had angle similarity. Since the triangles are similar, I'm going to set up a way to get their proportional sides. So specifically, then, let's go ahead and do, I'll do the little triangle first. Why? Arbitrary choice. So the little triangle is 6 over s for its side lengths. And again, why did I choose to put the 6 on top? Arbitrary choice. You could set this up as s over 6, and as long as you're consistent with that order in the next one, you're going to be okay. But since I chose to put the 6 on top, that means I put the height on the top. So when I do this next one, the height needs to go on top as well. So the 18 is going to be on top of this other one, and it's over the length, the width. Now, let's be careful here. What is the width of this? We're looking at the width of the big triangle. It is not 100. It's 100 plus s, yeah.
8.
Now, this is technically really all we have to do in order to now be able to find the derivative and get a derivative with respect to the time. Although, there's going to be something kind of weird here, right? Because if I find the derivative of this, notice my answer is just going to have s in it. How could I use this if it only has s in it?
Oh.
Ah. Remember how we said that we needed to put a variable name on anything that changes? That 100, I gave it a variable name, right? Remember we called the 100 d. So when I write the equation, actually, I'm going to actually write that as 100. I'm sorry, d plus s.
Wow. Which creates ds.
Now, when I find the derivative, you can see we will end up with a derivative of d involved. I'll be able to use the 8 to find my answer. Okay, so now we're heading in a good direction. Now, you could find the derivative here, but you'd have to use quotient rule. It'd be ugly. I don't want to deal with that. Let's simplify this equation before we get there. So go ahead and cross multiply and simplify what you can. So if I cross multiply, I end up with 6d plus 6s equals 18s. And again, I could actually move those s's together. So I subtract the 6s from both sides, and we end up there. And if you stop there, that is fine. Some of you didn't stop there, though. Some of you went ahead and said, hey, I can divide both sides by 6. And so I'm going to go ahead and do that. And you turn it into d equals 2s. That's perfectly fine as well. I did it that way because I like to simplify anything I can in advance. But either way is going to give you the same answer in the end.
What can we figure out what?
So now remember what we're actually finding here. We're trying to find how fast will the length of his shadow be changing. In other words, we're trying to figure out what is ds over dt. Since that's what I'm trying to find, I now want to go ahead and find the derivative of this equation with respect to t. And so when we do that, of course, the left side, that's just dd over dt equals 2 times, now the derivative of s, well, that'd just be ds over dt. Well, now we can actually find it. Remember, we're trying to figure out what ds over dt is. We know what dd over dt is. Remember, dd over dt, that's how fast d is changing.
That's 8.
It's 8. Go ahead and plug that 8 in for dd over dt. You end up with 2 times ds dt. Divide both sides by 2.
Equals 4.
And so we end up finding that the answer then is 4. Specifically, for what?
4 feet squared per second.
Feet
Oh, feet per second.
per second. Because remember, we looked to see what is the top measured in. S is measured in feet. The bottom was measured in seconds.
Oh.
So feet per second.
Oh, I get it.
That's our final answer. We're done there.
That's exactly what mine was.
So if I draw this out in picture, it ends up being very similar looking, of course, to the last one because it's the same kind of an idea. We got a lamp casting a shadow and a person whose shadow it is that's being cast. And we're being asked how fast is the shadow increasing. And so we're looking just for this distance here, which is going to end up being ds over dt because the rate at which s is changing. So we're looking to find that value. How quickly is the value of s changing? And so set up your equation. And again, when you set up this equation, because it's similar triangles, set up a proportion of the side lengths. Now I chose to set mine up in the same order that I did last time. Again, though, the order of your proportion doesn't matter as long as you're consistent within the order. You'll know it's the same when we actually solve it, so cross, multiply, and simplify as much as you can from there. And so when you cross multiply, you'll be looking at this, 1.8d equals 3.2s. Yes, you could try to simplify that from there, but I think most of you would have stopped there, and that's fine. You can go ahead and find the derivatives from here.
Wait, what if you actually solve?
And then once we've taken our derivative, we can go ahead and plug in the rate that we know, which is going to be this one down here. That's the dd over dt. And so when we actually do that math, we should get an answer of 0.675. That's from doing 1.8 times 1.2 first. Then divide both sides by 3.2.
I did the ratio.
Now, one little detail though, I don't want to leave this as my final answer. It's missing something. Units.
Units.
So, what is S measured in? Meters. So it's meters per whatever T is measured in, which is seconds. So then that is my final answer for it.